Modules and Homological Algebra, Lecture 18, Problem Session. Problem 1. For a non-negative integer I, denoted by I underlined, the set which consists of all elements 1, 2, 3, and so on up to I. So here 0 underlined denotes the empty set. Let C be the full subcategory of the category of all sets, whose objects are exactly these sets I underlined, where I is a non-negative integer. Prove that the category C is equivalent to the category of all finite sets. Solution. We prove that the natural embedding functor f from C to the category of finite sets is an equivalence. We construct the quasi-inverse G to f. So G is a functor from the category of finite sets to C as follows. For a finite set X with k elements, let us fix a bijection psi sub x from X to k underlined. We said that the value of G at X is equal to k underlined. So when X has exactly k elements. And for any function f from x to y, the value of g at this function f is the following function from the cardinality of x underlined to the cardinality of y underlined. So the function is the composition which starts from psi sub x inverse, then f, and then psi sub y. Let us first check that g is indeed a functor. For this we need to check that g applied to the composition of f after h, where f is a function from y to z and h is a function from x to y. So g applied to the composition of f after h should be equal to the composition of g of f after g of h. The left-hand side of this equality, directly from the definition, can be computed as follows. So if we apply g to the composition of f after h, then this is a composition of psi sub x inverse, followed by h, then followed by f, and then followed by psi sub z. At the same time, the right-hand side of this equality, that is g of f after g of h, by definition is the following composition. So g of h is psi sub x inverse followed by h, followed by psi sub y, and g of f is psi sub y inverse followed by f, and then followed by psi sub z. Since composition is associative, we can just ignore the brackets, and then we see that in the right-hand side, in the middle, we have psi sub y inverse, composed after psi sub y. We can simply delete this because this composition is equal to the identity, and then we obtain exactly the left-hand side. So this proves that the left-hand side of our equality is equal to the right-hand side and shows that g is indeed a functor. Note that the fact that g after f equals to the identity functor on C follows directly if we choose C sub I underlined to be the identity map on I underlined. So in order to prove that G and F are mutually quasi-inverse equivalences of categories, we need to prove that F after G is isomorphic to the identity functor on the category of finite sets. And in order to prove that, we will construct an invertible natural transformation from the identity functor on the category of finite sets to the composition of f after g. And in fact, we already have such a natural transformation. So our assignment xi, so the xi is an assignment which assigns to each finite set a certain bijection with the set of the form cardinality of the original set underlined. So this xi is a natural transformation from the identity functor on the category of all finite sets to the composition of f after g. Note that since our xi sub x is bijective for any x, this natural transformation is obviously invertible. To check the naturality of xi, we need to prove that the following diagram commutes for any function f from x to y. So we have the diagram. In the first row, we have f, which is a function from x to y. And then we have a map from x to the set of the form the cardinality of x underlined, which is exactly by definition the image of x under the composition of f after g. And the map between them is our chosen map xi sub x. Similarly, we have xi sub y from y to the cardinality of y underlined. And then in the second law, the horizontal map is f after g applied to our map little f. And this commutes since the value of the composition f after g applied to our map little f is by definition equal to the following composition: xi sub x to the power minus 1, followed by f, and then followed by xi sub y. And that is exactly the map obtained by going up here, and then by f, and then going down. So by definition, this diagram commutes, which means exactly that xi is a natural transformation from the identity functor to the composition of f after g. And this is exactly what we needed to prove. Problem 2. An object I of a category C is called initial, provided that any morphism set Cij is a singleton for any j in C. Prove that an initial object in a category, if such exists, is unique up to isomorphism. Solution. Assume that I and j are two initial objects in the category C, and we have the following four singletons. The set Cii is a singleton because I is initial, and it of course consists from the identity on I. The set Cij is a singleton because I is initial, and we assume that the set consists of some morphism which we call alpha. The set Cji is a singleton because j is initial, and we assume that the set consists of some element which we call beta. And then we have the set Cjj. It is a singleton because j is initial, and so it consists of the identity on j. Then the composition of alpha after beta, this should be a map from j to j. So there is only one such map, so it is equal to the identity on j. Similarly, the composition of beta after alpha, this should be a morphism from I to I, and there is only one such morphism, 1I, so this composition is equal to the identity on I. And this means exactly that alpha and beta are pairwise inverse isomorphisms between the objects I and j. And this shows that an initial object is indeed unique. Problem 3. Show that every epimorphism in the category of abelian groups is surjective. Solution. Let phi be a homomorphism of abelian groups from an abelian group A to an abelian group B. Assume that phi is not surjective. Then the image C of phi is a subgroup of B which is different from B. Note that this subgroup is a normal subgroup because B is abelian. We work in the category of abelian groups. And now we can consider two different homomorphisms from B to the quotient of B modulo C. Let us denote by pi the natural projection, so this is a surjective homomorphism from B to B modulo C. And then we have the trivial morphism, which we denote by sigma, and this is a homomorphism from B to B modulo C, which sends all elements in B to the identity element in B modulo C. Clearly, pi is different from sigma because B modulo C is different from the identity group. At the same time, both compositions pi after phi and sigma after phi are trivial homomorphisms, because the image of phi is C, and this is killed both by pi and sigma. Therefore, we have that pi is different from sigma, but pi after phi is equal to sigma after phi, which means that phi is not an epimorphism. Problem 4. Show that the abelian group Z2 is neither projective nor surjective as an object in the category of abelian groups. Solution. Consider the natural projection pi from the abelian group Z4 to the abelian group Z2. It is surjective, and hence it is an epimorphism. If Z2 were a projective abelian group, then the identity map on Z2 would factor through pi. So there should exist then a morphism from Z2 to Z4 such that its composition with pi is equal to the identity map on Z2. There are only two morphisms from Z2 to Z4. The trivial morphism, it always exists, and the morphism of multiplication by 2. So the morphism which sends 1 in Z2 to 2 in Z4. And postcomposing any of these two morphisms with pi gives the trivial endomorphism of Z2. So we cannot factor the identity map on Z2 through pi. This is a contradiction, and this shows that Z2 is not a projective abelian group. Now let us prove that Z2 is not an injective abelian group either. So consider the natural embedding I from Z2 to Z4, which is given by multiplication by 2. That's the map which we discussed on the previous slide. It sends the element 1 in Z2 to the element 2 in Z4. This is an injective map, of course, and hence it's a monomorphism. If Z2 were injective as an object in the category of abelian groups, then the identity map on the Z2 should factor through this monomorphism I. In other words, there should exist a morphism from Z4 to Z2, such that precomposing that morphism with I, we get the identity map on Z2. There are two homomorphisms from Z4 to Z2, the trivial morphism and the natural surjection. Precomposing any of these two homomorphisms with I gives the trivial endomorphism of Z2. So this is because the image of I belongs to the kernel of both these homomorphisms. And this gives us a contradiction, so the identity on Z2 does not factor through I, and I is a monomorphism, which shows that Z2 is not an injective abelian group. Problem 5. Let A be a finite abelian group. Prove that the tensor product of A and Q, where Q is the group of all rational numbers under addition, is 0. Solution. Recall that the identity element in the tensor product of two abelian groups X and Y coincides with any generator of the form X tensor 0 and with any generator of the form 0 tensor Y, where X and Y are elements in X and Y correspondingly. Let W be any non-zero rational number, and let A be any non-zero element in our finite abelian group A. Then, by Lagrange theorem, if we take our element little a and multiply it with the cardinality of the group, we will get the zero element in our abelian group capital A. So now let us do the following computation. Consider the generator W tensor A in our tensor product of A with the rational numbers. Note that in the rational numbers we can divide by any non-zero number, so we write W as W divided by the cardinality of A and then multiplied with the cardinality of A. Now, using that in the tensor product, we can move integer multiples from left to right, The same element is equal to W divided by the cardinality of A, tensor with the cardinality of capital A times the little a. And this is equal to W divided by the cardinality of the capital A, tensor 0. Which means that any generator in our tensor product is equal to 0. So our tensor product is indeed the trivial abelian group. Problem 6. Prove that the forgetful functor f from the category of groups to the category of sets has no right adjoint. Solution. Assume that G from the category of sets to the category of groups is the right adjoint of our functor f. Then, by definition, there are bijections for any group H and any set X between the set of all maps in the category of sets from f of H to X and the set of all group homomorphisms from H to G of X, and these bijections are natural both in H and in X. So let H be a singleton group, so the trivial group. Then, of course, from a singleton group to any other group, we have a unique homomorphism, which is just the map which sends the identity in the singleton group to the identity in the other group. That is it. So the set of all group homomorphisms from H to any group K is a singleton for any group K. In particular, this is a singleton for any group of the form G of X, where X is a set. At the same time, on the left-hand side of our bijections, we have the set of all set maps from f of H to X. So f of H is a singleton, it's just the restriction of a singleton group to sets. And now the set of all maps from a singleton set to a set X, it has the cardinality of X elements. And this gives us our contradiction, because in our isomorphisms, the set on the left has cardinality of X elements, and the set on the right has one element. So this is not possible, which gives us our necessary contradiction and completes the proof. Problem 7. Let A, B, and C be abelian groups. Prove that the tensor product of A with the direct sum of B and C is isomorphic to the direct sum of the tensor product of A with B and the tensor product of A with C. Solution. Consider the group homomorphism phi from the left-hand side to the right-hand side. So it's a homomorphism from A tensor with B plus C to A tensor B plus A tensor C. And we define this homomorphism phi on the generators of the domain such that it sends A tensor B comma C to the pair A tensor B comma A tensor C. We need to prove that this is well defined on the generators. So on the generators, we need to check the defining relations for the tensor product. So if we take the element AN tensor BC, where n now is an integer, this element is sent by our definition to the pair AN tensor B, comma AN tensor C. Again, from the definition of the tensor product, for both components in our pair, we can move n from left to right. So this is equal to the pair A tensor NB, comma A tensor NC. And this is exactly the image of the element A tensor, the pair NB and C. And this is now NB and C is a pair in a direct sum, and we can move n out, and we get the element A tensor n times the pair B, comma C. And this completes the proof that our map phi is well defined. Now consider the group homomorphism from the right-hand side to the left-hand side, which we call psi. So this is a map from the direct sum of A tensor B and A tensor C to the tensor product of A with B plus C. And we define psi on the generators such that it sends the pair A tensor B, comma A tensor C to the tensor product of A with the pair B, C. Again, we have to check that this is well defined on the generators. So if n is an integer, then the pair an tensor B, comma an tensor C is sent to the element an tensor bc. In the latter, we can move our integer n from the left-hand side to the right-hand side of the tensor product to get the element a tensor n times b, comma c. And now n times b, comma c is equal to nb, comma nc, because this is how the operation is defined in the direct sum of two groups. So we get the element a tensor, the pair nb, comma nc. And this is exactly the image of the element a tensor nb, comma a tensor nc in our domain of the homomorphism psi. So this shows that psi is well defined. Then, directly from the definitions, we see that both compositions phi after psi and psi after phi are the identities on the generators. Since these compositions are the identities on the generators, it follows that they are the identities. And this proves that the left-hand side in the formulation is isomorphic to the right-hand side via these two isomorphisms. Some problems and questions at the end. Question 1. Prove that a terminal object in a category, if exists, is unique up to isomorphism. Question 2. Show that any non-singleton finite abelian group is neither projective nor surjective as an object in the category of abelian groups. Question 3. Let A be the multiplicative abelian group of all complex roots of unity. Prove that the tensor product of rational numbers with A is 0. Question 4. Let A be the multiplicative abelian group of all complex roots of unity. Is A projective or injective in the category of abelian groups? Question 5. Prove that the tensor product of B plus C with A is isomorphic to the direct sum of B tensor product with A plus C tensor product with A for any abelian groups A, B, and C. Thank you very much, and see you next time.